So good morning, everybody. So again, it's our pleasure to welcome Professor Giles Hammond from the University of Glasgow along with us this morning. Giles obtained his PhD in the year that dark energy was discovered. That was the year 1998. Yeah, you're right. His research was not on that.
It wasn't on that, though. Excellent. So it could, who knows? Let's watch this space.
Yeah. His research was focused on building superconducting torsion balance to search for violations of the equivalence principle and perform precision measurements of the Casimir force. He spent 2 years at GILA, University of Colorado in Boulder, building inertial seismic isolation systems for the Advanced LIGO gravitational wave upgrades. In 2007, Giles moved from Birmingham to Glasgow. He works in the development of ultra-low thermal noise suspensions, operating both at room temperature and cryogenic temperature. Giles led the team that developed, installed and characterized fused silica suspension systems in Hanford and Livingston gravitational wave detectors, all that technology that gives you low frequency sensitivity, which was mighty useful given the fact that binary black hole mergers were out there waiting to be observed. Giles also leads an activity within Glasgow, or the Glasgow-led Quantum Technology Hub in quantum enhanced imaging, has pioneered the development of a new type of gravimeter-based MEMS technology, providing a transformative new way to image the local gravitational field with applications in volcanology, environmental monitoring, and defence. And so it's with great pleasure we welcome Giles Hammond.
Thanks very much. Pleasure to be here. Thanks to the organisers for having me to give these couple of lectures. So I'm going to do a couple of things today. So the first slide, probably, I guess it's going to be an hour and 20. I'm going to talk about suspensions for advanced LIGO. So these are the fused silica suspensions, but I also talk about seismic isolation. How on earth do you, at 10 hertz, get 10 to minus 19 of a meter in terms of reducing seismic noise and reducing thermal noise? And then the second lecture, as Stuart had mentioned, I lead this activity on MEMS gravimetry, a field that I started off with a colleague in engineering about four years ago. So I want to tell you a little bit about that, because it's a nice example of where you take this very fundamental core technology in gravitational waves and you kind of spin it out into a more applied field. So that's another side of the work that I do. But let's talk about suspensions to start with, and we'll kind of talk for about an hour or so, then we'll have a wee break, and then we'll have another kind of 50 or so minutes. So I'm going to talk about the suspensions, but it's important to know when you're designing these things, what are you designing to? What are the requirements for the suspensions? Talk a little bit about what seismic noise is and what thermal noise is. You might have already heard about that in the lectures last week. How do we build these suspensions? They're made entirely out of fused silica, so silicon dioxide, amorphous glass. So how on earth do you actually make these suspensions? And once you've made them, how do you actually model them and know that they're actually going to give you 10 to minus 19 of a meter at 10 hertz? Or I should say 10 to minus 19 meters per root hertz, so we'll talk a little bit about the units as well. And then I'll spend a very short time just talking about some of the kind of future developments, because it's important to know where we are currently, but also where we're going. What's the next kind of step in the field for third generation detectors? You've kind of heard about this, so I will not go through this slide in much detail. So top right is the torsion balances that I used to build. So these were looking, for example, for does an electron spin up or spin down, fall in the same way in a gravitational field? So if you like, this was searching for mass spin coupling forces mediated by axions. Axions are really tough to detect. We didn't see any, but we put new limits on those types of forces. Bottom left is the advanced LIGO seismic isolation systems. Bottom right is the MEMS stuff. I'll talk about that a little bit later. And top left, of course, is the fused silica monolithic suspensions. And that's really a kind of activity that was pioneered by not just Glasgow, but the UK. So Advanced LIGO UK was really kind of tasked with developing the suspensions for the Advanced LIGO detectors. So a real key piece of hardware to suspend these 40 kilogram mirrors in as quiet a way as possible. So you've probably seen that before. So Andreas will have talked to you about the optical simulations. So that's, of course, the Advanced LIGO interferometer. In reasonable level of detail, it does not have every optical component on, of course. But the main things are, for example, on the left, the laser. Actually, Stuart, do you have a pointer?
Oh yeah, sorry.
So on the left there, there's the laser beams. That's neodymium YAG laser. A design sensitivity will be about 100 watts, pumping into the mode cleaning cavity. And then, of course, you go into the main interferometer. So sitting right in the center there is a beam splitter. Here's a beam splitter. And then, of course, these are your 2 arm lengths. These are the 4-kilometer arms. So these are the fabric power cavities that make up the interferometer. And of course, thank you. Of course, you can't build arms as long as you'd like on Earth. If you think, I'd like to detect a wave around 100 hertz, then you say, well, what's the wavelength of that? Then you say, well, c equals f lambda, and c equals 3 times 10 to the 8, and f is 100 hertz, so that's 3 times 10 to the 6. That's the wavelength. You're not going to build that on Earth. So you kind of use this trick of combining the interferometer with fabric power cavities in the arms, and you have maybe a finesse of 400, 450, so you get some kind of bounce. The photon stays in that cavity for a time that allows it to interact with the gravitational wave. And this detector is so that it's held just off a dark fringe. So it's not quite on the dark fringe, it uses DC readout, but it's held just off the dark fringe, which means most of the light actually doesn't go to the output port, but it goes back towards the laser. So you have this power cycling mirror that pumps that light back into the interferometer. So there's a power cycling gain, and that makes your laser look more intense than it really is. So certainly design sensitivity, you'll be storing 800 kilowatts of laser power. In initial light, goes about 10 kilowatts of laser power, and that's a real challenge. Storing that much power in the detector, because there is absorption in these mirrors and you get thermal lensing. So this is one of the reasons why squeezing of the light field is so important, and I think you'll hear about that a little bit later today. And then, of course, there's your output detection. That's your output branch, the signal recycling mirror, which allows you to make this device. You can run this interferometer broadband, or you can actually have a signal recycling mirror where you actually tune the interferometer. And to start with, it's a broadband detector, because you don't know what you're looking for. So this is kind of a bit more detail. So all of these components have suspensions. I'm only going to talk about the kind of main ones, the core optic suspensions, in any detail, but you have to suspend everything in there. Because ground shakes, at 10 hertz it's moving at about maybe a nanometer. And you need to get to 10 to minus 19 for the core optics, so you need 10 orders of magnitude of isolation. So the way that you do that is you suspend these core optics, the end test masses and the input test masses, on multiple stage pendulum suspensions, and that provides seismic isolation. And if you do it the right way, you can also get reduction in the thermal noise. So you need to suspend that 40 kilogram mirror. It needs to look like a free test mass above 10 hertz, but it cannot be moving by more than 10 to minus 19 of a meter. But you also need to suspend the beam splitter. It's not quite as stringent as the core optics components, because these are really kind of sitting in the fabric power arms of the cavity. So it's about an order of magnitude lower requirements on the seismic noise and the thermal noise. And that means for the core optic suspensions, you need to hang them on 4 stages of pendulum isolation, with the final stage just being made entirely of glass. For the beam splitter, you can get away with a triple suspension, and the final stage being made out of metal. And then you've got the output, what we call the output mode cleaner of the interferometer. That's a 2-stage pendulum suspension. These signal recycling mirrors, so these have to be on what we call triple suspensions. So there's 2 varieties of triple suspension. There's a small one and a large one. The small one's a little bit shorter, doesn't have quite the isolation of the large one, but it's a little bit easier to make. Also the power recycling mirrors, all of these 3, they're held onto triple suspensions. And all these input optics here, the input mode cleaner, so these are the ones that clean the spatial mode of the laser beam. It's a little bit like a low pass filter of the optical light field. So they all have suspensions. So when you see the kind of drawing there, and you say, well, that's fine, all of these optics have to be suspended from the ground. And that's an interesting control problem, because all these optics have multiple degrees of freedom. So a quad pendulum suspension, which has got 4 stages, each stage has got 6 degrees of freedom. 3 linear, and then 3 angular. So 6 degrees of freedom. So you've got 24 degrees of freedom to control in that pendulum suspension. Just an alternative view, just to show you, actually that's what chambers really look like in advanced LIGO. So some of them don't have a lot in, so things like the core optic component, they only have like the input test masses, and these little plates here, these are called compensation plates. So these are plates where you can actually kind of shine a carbon dioxide laser onto the front surface to actually change the optical path length, and change the, for example, if you get thermal lensing of the beam inside this cavity, you can actually compensate that outside the main interferometer cavity. You've got the beam splitter here. These ones are fairly easy to work with because they've only got a few components in. This is output mode cleaner, this is suspended, this is a monolithic piece of fused silica. But some of them are rather busy, so this is a real nightmare. HAM2 is so HAM is what's called a horizontal access module. It's a real nightmare to work in. I kind of mainly work I just work on these suspensions here, so I don't have to worry about what's in there. But when you're doing beam tracing, understanding scattering of light between optical components, it's a real challenge because this one houses part of the mode cleaner here, and then of course you go through the Faraday isolator, and then you go into the power recycling mirror. And the Faraday isolator means that any light getting back here doesn't go back towards the laser, which is not a good thing to do. So, bottom line, what are we trying to do? What does a suspension system do? Well, it kind of does those things that I've written up there. It supports the optic. That's the first thing it has to do, but it has to support it in a quiet way. So it has to provide low thermal noise, and it has to provide low suspension noise. Those are the two kind of top-level requirements. But it needs to do a few other things. We need to control the position of the optic, so we need to be able to tilt it and move it. Because 4 kilometers away, there's another mirror. So you say, well, okay, I'll shine this and I'll try and hit the wall. And that's okay, I'm fairly stable over, a few meters. Try and do that over 4 kilometers, it's a bit tough. You have to get sort of nanoradian precision. So if you say, well, I want to hit the beam spot within a few millimeters over 4 kilometers, so that's about 10 to minus 3 over 4,000. Yes?
I have a question regarding the last slide. When you say they're modules, does it mean that every one of them is separately actively isolated?
Yeah.
Or?
Yeah. I'll talk about it a little bit later, but each suspension, well, it's interesting. So each suspension can work on its own, so we call that local control. So they're locally damped, but the core optic and the one 4 kilometers away, they have to kind of talk to each other. So there's global length control signals and angular control signals, which are derived from the interferometer. So there's a combination of local control, but also global control. So I'll have a slide on that later, we'll pick up on it. We also want to provide the damping and the control of the low frequency suspension modes. And as I said here, we want to maintain some way of, how do you hold the arm length of the interferometer to 10 to minus 19 of a meter, where you need kind of control signals, which are essentially the interferometer fringe readouts, and kind of angular control signals, which are Hartmann wavefront sensors. And those get fed to the suspensions, which allow you to change the position of the suspension to keep the interferometer on lock. Because lots of things are trying to change the length of the interferometer, and you're always trying to hold it on a resonance. We need to interface with the seismic isolation system. We need to hold the optic so if there's an earthquake, and there's quite a lot of earthquakes up in Hanford, the suspension doesn't fall apart. So it goes into this mode where it actually locally damps the suspension. And as we talked about earlier, these compensation plates, we need to have some way of providing a compensation scheme. So as well as a compensation plate around the outside of the test masses, there's what we call a ring heater, and that locally heats up the test mass to take account of the fact that you're heating in the center of the laser beam, but not towards the outside, so that the mirror kind of starts to warp itself. These are just the numbers, the requirements. So in terms of suspension thermal noise, I've kind of mentioned it before, it's 10 to minus 19 meters per square root of hertz. And that's at 10 hertz. That's the most stringent requirements, and that's in the longitudinal, along the length of the interferometer. Vertical also couples into horizontal, because the interferometer arms are along they hang along the local gravitational vertical. So essentially, you have your interferometer arms They would like to do that, where that's local G. But actually you can't do that, you actually have to hold them. So you apply control forces to actually hold them so that the photons traveling in a straight line here. So actually any vertical motion couples, if you've got vertical motion coupling this way, it does couple a small amount into the horizontal direction. So we have to worry about the vertical motion. So there's a requirement on the vertical about 10 to minus 16 meters per root hertz. And that assumes there's about a coupling of one in 1,000 or 0.1% from any vertical motion into the cavity. In terms of seismic noise, it's exactly the same requirement. So it actually doesn't make sense if you hit a thermal noise of 10 to minus 19 meters per root hertz, your seismic noise should be about the same. It doesn't make sense to make it 10 orders of magnitude smaller because you can't use that anyway. So both of these requirements go together, seismic and thermal. There's other requirements on the pitch and yaw. So when I talk about pitch and yaw, pitch I mean kind of moving backwards this way. Yaw is kind of out of the plane. And they're related to beam centering. That you assume they're about a millimeter. The beam is centered to about a millimeter. It's sometimes a little bit worse than that. But 10 to minus 17 radians and a millimeter, that gives you about 10 to minus 20 of a meter per root hertz. So it's one order of magnitude lower than the longitudinal or the vertical. So these are top level requirements. These are sort of the secondary requirements. And there's a whole bunch of other noise sources like actuator noise, sensor noise, noise due to magnets on the suspension, and those have to be 10 times lower than the longitudinal thermal noise. So these are what we call technical noise sources. So that's what we have to design to when we're building. What did initial LIGO look like? Well, initial LIGO was a vacuum tank with passive isolation stacks and a single mirror held in a single wire loop of metal. And that didn't provide much isolation below 40 hertz. Advanced LIGO wanted to get below 40 hertz to around 10 hertz of the lowest operating point. So it required some real kind of significant change. So the things that you see here, there's pillars here. So this is the ground, and then the ground is essentially this point here. So the ground's moving at about a nanometer per root hertz at 10 hertz. There's kind of out of vacuum hydraulic external stages here on the outsides of the piers. Those take out the large motion. So for example, every day the interferometer is kind of wanting to change length by about 400 microns, and that's due to the earth tides. So you need to take that motion out because you need to hold your cavity on lock. So you do that outside the vacuum system with hydraulic external actuators. And then everything inside the vacuum is this here. So this is a two-stage active passive isolation system. And that provides about a factor of 1,000 isolation at 10 hertz. So you go from about 10 to minus 9 down to about 10 to minus 12, maybe a few 10 to minus 13. You've still got 6 orders of magnitude of isolation, and that's all done with this quadruple pendulum that's hanging underneath the isolation system. So you can see there's multiple systems. There's one stage of isolation outside. There's 2 stages of isolation in vacuum here in terms of the seismic isolation, and then there's 4 stages in terms of suspension. So 7 stages in total. And that's of course how you get from 10 to minus 9 to about 10 to minus 19 of a meter per root hertz. That shows a little bit more detail, just the suspension. So on the left here is an initial LIGO. So that was about a 10.7 kilogram piece of fused silica. And that was hung from, you can just about see here, a single loop of wire going around here. This is a single loop of metal wire. To actually access the improvement in the seismic isolation and thermal noise performance in advanced LIGO, then the lower stage, the entire lower stage there, was replaced with what we call the fused silica monolithic stage, and this is entirely made out of glass. So we have the test mass, here's the test mass here, this is 40 kilograms of fused silica, and this is what we call the penultimate mass, also 40 kilograms of fused silica. And then we suspend that with 4, you can just see here, 4, 2 on here, 2 on this side, 4 fibers of fused silica. So the entire system on the right looks like it's made out of a single piece of glass. And what we have to do is you have to produce these fibres, so we have to pull these fibres, we have to attach these ear attachment points onto the side of the test mass. I'll show a photo a little bit later of that. So we do that with hydroxycatalysis bonding, and then we take the fibres and we weld them to the ends of the pieces of silica, and we develop a full noise model of that suspension system. And I'll show you some data from the suspension a little bit later, but these fibres under tension, they have what we call violin modes, and they're extremely low mechanical loss. So if you pluck one of these with a thermal vibration, they take many, many days to ring down to 1/E. Typically at the moment about 10 days, 11 days to ring down in vacuum. So extremely low mechanical loss. I've talked a little bit about these kind of units, meters per root hertz. So actually, hands up. When I talk about meters per root hertz, have you actually had a discussion of what a meter per root hertz is? Hands up if you're happy with that. Okay, so some of you. Okay, well, I have a slide, so I'll go through it. But for some of you, you'll have seen this before. We often talk we talk in terms of meters per root hertz for displacement noise, or in terms of strain sensitivity of the detectors per root hertz, 1/root hertz, and that would be a strain because it's a delta L over L, so it's a meter per root hertz over a meter. So when we think about kind of signals, so imagine that this is a MATLAB simulation. Always go to MATLAB if you want to kind of try something out. It's a good thing to do. So here I've just generated some random noise. So this is using rand from MATLAB. So you do, well, it's hard to tell, but this will be going between plus and minus 1. So it'll be minus 1 plus 2 times rand. And that'll generate a random number. And I do that a bunch of times. And I just plot out the data. So this is a random generated time series. And that's what we all aspire to when we build experiments. We would like to see what we call random data, random noise, which we sometimes call in the frequency domain white noise. So you can think in the time domain, which is here, and you think in terms of an amplitude, which is in the meters, and it's as a function of time. So of course you could take that data set and you could say, well, what's the RMS of that data series? What's the root mean squared? So if this was about 0, you'd say, well, the mean is 0. So each data point, you'd take it, subtract it from the mean, square it, and take the average of all that data, and that'd be your RMS when you square root it at the end. Well, of course, you can take the you can kind of convert that into the frequency domain, and we do that with a Fourier transform or fast Fourier transform, an FFT. And MATLAB's fantastic for that. So there's a function, if you've not used it before, I shall even write it down because it's so useful. P Welch. So that's a function in MATLAB, and that does a Fourier transform or fast Fourier transform. And the great thing about that is it's calibrated. So the units on the axis are actually calibrated correctly. Because that's a tricky thing in Fourier transforms, is to actually get the units right. But in terms of units, this is, if it was an amplitude spectral density or an ASD, then the units would be meters per square root of hertz. Sometimes we talk about power spectral density or PSD, and that units would be meters squared per hertz. And all that's saying is, rather than the time domain view, which is on the top here, we're now in the frequency domain. So this is meters per square root hertz as a function of frequency now. And then you say, well, okay, I already worked out the RMS of my data. What about the root mean squared of this data? Well, what you do is you just say, well, because this is random noise, then this is what we call white noise. So it's got equal contributions at all frequency. So it's amplitude spectral density, so its power spectral density is flat. So what you can do there is you can work out the area under this, more generally a curve, but in this case it's just a box. So the way you do that is you say, well, I'll take the output here, which is in meters per root hertz. I shall square it, so I'll turn it into a power. So that'll be meters squared per hertz, and I'll multiply by the bandwidth over which I make the measurements. So there's an upper bandwidth, and of course the upper bandwidth is given by the Nyquist sampling frequency. And then the lower bandwidth is given by 1 over the total length of the record. So when you work that out and you say, well, I'll square the amplitude spectral density, meters squared per hertz, multiply by the bandwidth, hertz, I get meters squared, take the square root of it, I get meters. And it will not surprise you that that number and that number are exactly the same thing. So That's the way of getting the RMS from the time series or the RMS from the frequency series, and that's of course Parseval's theorem. That's exactly what Parseval's theory says. You can take a time series, you can take the equivalent kind of frequency series, and the sums of the squares of the Fourier coefficients, which in this case is the area under this curve squared, is the same as the time series, so it's the RMS of the data series. So that's why we have these units meters per root hertz or meters squared per hertz, because it's just a frequency view of that picture. It's interesting because when you look at LIGO and you say, well, we operate here, okay, I've kind of simplified it, I've said it's white noise. It's not really white noise, because any kind of drift or long-term variation means that this noise kind of kicks up at low frequency. It might be 1/f noise. And we kind of call noise, well, white noise is flat, pink noise is like 1/f, there's red noise, brown noise, all different colours of noise depending on the exponent of the frequency. But actually what you're doing is you're working with advanced LIGO in this band here, for example, but actually everything that contributes to the total motion of the mirror is somewhat sometimes out of band. So you might go from 10 hertz up to a few kilohertz, but actually a lot of the motion for advanced LIGO comes from low frequency. So you look at the seismic spectrum, there's a big peak at about 0.16 of a hertz. Although it's way out of the band, it gives you RMS motion. And if you want to lock your interferometer, you have to get rid of that motion. So that's why seismic isolation has to work down not just to 10 hertz, but all the way down to a few tens of millihertz. So there's a couple of things that we really worry about when we're looking at seismic in advanced LIGO. So first is the earth tides. So twice a day, we're here at St Andrews. If you look out the window twice a day, you'll see the tide coming in and going out. And that's of course due to the tidal potential of the moon and the sun. But also, it doesn't just, we don't just see water tides, but we see the solid earth tides as well. So the tidal potential stretches and shrinks the earth. So twice a day, at the equator about 40 centimetres, the radius of the earth changes. And that means little g changes. Or the strain in the earth changes. And advanced LIGO is really good at picking that up. So over 4 kilometres, you can get a few hundred microns of shift due to the earth tides. And they're low frequency, they're twice a day. So diurnal or semi-diurnal. So it's 10 and 20 microhertz. That's what the hydraulic external actuators are for. At the microseismic peak, this is about 0.16 of a hertz. This is a big peak in the seismic spectrum due to ocean waves crashing onto the continental shelf. That gives a big peak in the seismic spectrum, and you have to isolate at that. So that's quite a hard thing to do. And the way that we do that is not just by hanging on multiple pendulum stages. That works really well at 10 hertz. But actually, to get isolation down at the low frequencies, we need active isolation. We'll talk briefly about that as well. So what we're saying is that seismic noise is a challenge. Even at a quiet site, it's a few nanometers, and at the Livingston and Hanford sites, it's a few nanometers per root hertz. So you might say, well, what happens if I take a single pendulum and I kind of shake the ground? So there's my single pendulum. And I say, okay, I'll shake the ground with an acceleration. What's my mass doing? What's the acceleration of my mass? Of course you can work that out because you can write down the second order harmonic oscillator and you can solve that. And then you might say, well, what happens now if I take the same system, but now I attach two pendulums, M1 and M2, where the total length is still the same. That's L, L1, L2. L equals L1 plus L2. Well, interestingly, if you take a single pendulum, which is the blue one there, and you get a single resonance because it's a single longitudinal oscillator, so you get a single resonance and it drops off as 1/f squared. If you take your double pendulum of the same length, then you get two resonances, because it's a coupled system, it's got two masses on the spring, and then it drops off not as 1/f squared, but 1/f to the 4. So every stage of isolation, it gives you 1/f squared to the power n, where n is the number of stages. So 2 stages, you get 1/f to the 4. 4 stages, the quad pendulum, you get 1/f to the 8. So for example here, this is a transfer function of the quad pendulum, and this is the magnitude, this is just unity here, this is 1. And then these are the body modes of the different suspension masses. Above is about 1 hertz. This is 10 hertz. This is where advanced LIGO wants to operate. So the body modes are around a few hertz. So here's a 3 hertz mode. This is 1, 2, 3, 3.5 hertz. And then off here, you're dropping over 1/f to the 8. So if your body mode's around 3 hertz, you want to operate at 10 hertz, then you get 10 over 3, which is 3 to the power 8 of isolation. And that's how you start to get a factor of 1 million of isolation, which gets you from 10 to minus 13 of a meter down to 10 to minus 19 of a meter per root hertz. So we use 4 stages of pendulum isolation. At the low frequency, that's harder to do because this, making pendula that work at 3 hertz is okay because they're about this long. Making pendula that have a resonant frequency of 10 millihertz is not really very practical. So you have to use some tricks. So what we do is we actually put onto our isolation systems we put seismometers. So what we're doing here's the ground, and your platform is a mass on a spring. That's all it is. So the platform has a resonant frequency. That's a mass on a spring. Okay, it's a gravitational spring, but it's still a mass on a spring. This is a traditional mass on a Hooke's law spring. So it's got a resonant frequency, and you put a seismometer on here or some sensor, and you look at the position of that mass relative to your sensor, and then you apply a filter. And then you take that filter and you put it through an actuation, and you apply it back onto your mass. And that's what we call a feedback system. So in LIGO, we take seismometers, and those are measuring how close we are to an inertial reference frame. That's what a seismometer is doing. And then we close this feedback loop. So we close a feedback loop onto the mass, and we push on the mass with these core magnet actuators. So on the test masses, or penultimate masses that you saw, we have magnets. On a reaction chain, we have coils, and we apply forces between them. And that allows you to apply active control. And these seismometers do work down to about 10 millihertz, so you can get about a factor of 10 isolation at the microseismic peak at 0.16 hertz or 160 millihertz. So that's a combination of passive isolation, which is just masses on springs, but also active isolation. And as well as feedback, which is kind of taking the output of the sensor and feeding back. If you know your mass spring system really well, and you measure the ground, you can actually do what's called feed forward. So you can take the output, feed it back onto the actuator, and this actually reduces some of the kind of control requirements on your feedback loop. So we use all of these tricks in both seismic isolation and the suspension systems in advanced LIGO. That's a picture of the advanced LIGO, what's called the ISI, the Inertial Seismic Isolation System. Of course, this is a clean area, so everything's kind of machined metal. But what you've got here, these are sort of the springs on the side here. So you're supporting these. This is the top stage. This is one of the pods for a seismometer here. And then on the underside, which you can't see, which would hang the quad pendulum suspension off it. So these provide about a factor of 1,000 isolation at 10 hertz. Okay, thermal noise. So we've talked a little bit about seismic. What about thermal? Because that's one of the requirements of the suspensions as well. So we see many types of thermal noise. So if you take a pendulum suspension, then it can vibrate in many ways. So it's got body modes, and we said that you take a single mode, a single pendulum suspension, it's got 6 degrees of freedom. So for example, it can go backwards and forwards in a longitudinal mode, this one here. The violin mode, so this is a fibre here, can bounce backwards and forwards. So there's a pendulum mode, there's a violin mode. The mass itself might actually be sort of stretching and shrinking, so this is an internal resonance mode of the test mass. The mode can be going up and down, it can be tilting, it can be yawing, pitching, yawing, anything it wants to do. And each of those modes, of course, has a thermal noise associated with it. So we have to manage and understand how do we make low thermal noise oscillators. So what we do in general is we make the mirror suspensions out of as low mechanical loss material as possible, and that's why we use glass in the advanced LIGO system. And I'll kind of go through a brief derivation in a few slides' time, where it shows you that actually having very low thermal noise is obtained by using high quality factor material. So although you're fighting against the thermodynamics, you're fighting against KT. Advanced LIGO operates at room temperature, so KT of thermal energy is around there. Okay, you could cool the detector down to reduce T. That's one way of lowering the thermal noise. But if you can't do that because you've got a room temperature detector, all you can do is you can decide to manage where you put that KT of energy. So what we do is we use very low loss materials, and that takes the energy of the resonant mode, in this case might be a pendulum mode, The purple one is a very low quality factor material, because you can see there by this sort of rounded bump, it's very shallow. And actually the interesting thing is, imagine you're operating at 10 Hertz here and this is your thermal noise performance. Well, the purple one isn't as good as the blue one. And you might say, well, what's the difference with the blue one? Well, the blue one's got much sharper resonance. So what we're doing is the blue one is using a very low loss material like glass. The purple one might be a low Q material like metal. What you're doing is you're taking that kT of energy and putting it, you're dumping it essentially all in the resonant mode. Okay, you can do something about that because you can actually damp the resonant mode, so you can do active control. And as long as you do it correctly, you don't inject new noise into the system. So you can deal with this high resonance, you can damp it and not introduce thermal noise into the system. But actually an interesting thing is at 10 Hertz where you're operating, you're down by a couple of orders of magnitude. So this is the game that we play. You say, well, okay, we can't beat thermodynamics with a room temperature detector, but we can decide where to put that energy. So the use of long, thin, fused silica fibers is the way that we kind of battle against thermal noise. And using very low loss bonding techniques like hydroxycatalysis bonding, and this is the way that we can actually manage the performance and improve the performance of detectors down to 10 to minus 19 meters per hertz at 10 hertz. So when we're looking at thermal noise, we're really thinking about the statistical motion of particles. So you might not have thought about test masses in gravitational wave detectors, but you might want to think about dilute gases. So even the gas in this room, the molecules are moving around, but they're moving around with a spread of velocities. So there's a Maxwell-Boltzmann distribution, there'll be a mean velocity and there'll be a spread of velocities. So when we're thinking about gravitational wave detectors, we think about the interaction between the test mass and that, for example, dilute gas, because if you don't pump out the system, you'd have gas damping. And of course, this was first, sort of looked at. By when we think about Brownian motion. So this is kind of really the fact that we've got kT of motion per degree of freedom, and that's distributed between kinetic and potential energy. So it's hard to see here, but you can see, there's these sort of fat droplets suspended in milk, and they're vibrating around. They're doing a little bit of a random walk because they're interacting with with thermal vibrations set up in the liquid. When we think about the gravitational wave detector, we have this mass. If you think about gas damping, we have this mass which is 40 kilograms, and it's suspended by fibers. And let's say it's moving with a velocity in that direction. Well, there's gas molecules that are bombarding it from different directions. And they have a range of speeds, but let's call it Vg, V gas. And there's some hitting from this direction. Well, on the whole, the same number hit from both directions. But the ones moving, because the object is moving to the right here, the relative velocity, the kind of impact velocity of these ones onto the test mass and these gas molecules on the test mass are different. And that's the origin of gas damping in a system. When you look at that, you end up with a force that's proportional to the velocity of the test mass. It's just momentum exchange between the gas molecules and, in this case, the 40 kilogram optic. So when we think about fluctuation dissipation theorem, there's usually, this was really developed by Callan and Welton. There's the idea that you have a fluctuation in a system, and that's related to the dissipation in the system. So in this case, we have the dissipation is the gas molecules hitting the side of the test mass, but that also gives rise to a fluctuation, because when that test mass is stationary and you get bombardment of the gas molecules, you can get momentum exchange, so you get motion of that test mass at the same time. So you might have seen the more familiar example is Johnson noise in a resistor. So if I build an amplifier with a resistor in it, and I say, well, what's the noise of my amplifier? Then you end up seeing, if you build the amplifier correctly, you'll just see the noise due to the resistor. So if you take a 1 megaohm resistor, for example, and you say, what's the voltage across it? What voltage do I measure with a spectrum analyzer? Well, you don't measure 0, but you measure an RMS voltage. And essentially the resistor has dissipation, so it's got a resistance, a megaohm. That's the dissipation, and that results in a fluctuation. In this case, it's a fluctuation of the voltage. So you see what's called Johnson noise, which is shown down here, which is the mean squared fluctuating voltage across a resistor, is just 4kT times the resistance times the frequency bandwidth. So if you work this out, this has got units of volts squared. This is hertz. This is volt. If I divide by delta F, I get volts squared per hertz. Remember that? We've talked about that before. So the mean squared voltage, if I like, is volts squared over delta F, and that's volts squared per hertz, power spectral density, and that's equal to 4kT times R. And if that's 1 megaohm, that's about 130 nanovolts per root hertz. That's very measurable in an amplifier. So we worry about, for example, Johnson noise in our resistors, and that's due to just thermal fluctuation. So in suspensions of gravitational wave detectors, we have dissipation as well, and the more general theorem which we'll go through is this one here. This is called the fluctuation dissipation theorem, and this is the fluctuation on the left-hand side. You've got 4kT in there, and then you've got the real part of the impedance, and the impedance is the thing that kind of brings together the dissipation part. So for a resistance, that's just voltage over current, and our fluctuation is a voltage, and our impedance is an ohm. But in our mechanical system, our fluctuation is typically a displacement, and our impedance is a mechanical impedance, which is force divided by velocity. So there's a very nice way of thinking, if you think about LCR circuits and you think about mass spring systems, they're actually completely analogous systems. Whereas one you've got a fluctuating voltage, the other you've got a fluctuating force. Where one you've got a fluctuating current, you've got a fluctuating displacement or velocity. So you can write an impedance for your LCR systems, you can write an impedance for your mechanical system. This is your homework if you want to go through that. It's always good to go through these things. I'll go through this quite quickly, but it's just a brief derivation to show you where you get to. So the most general type of Hooke's law system is F equals Kx, but our spring's a little bit different because we want to allow for the possibility of there being mechanical dissipation. So in our spring system, we've got force equals the spring constant, not just times x, but we've got this sort of extra term here. That's saying that if we apply a stress onto our spring, the strain doesn't necessarily need to be in phase. And indeed, in a resonant system, the difference between the kind of driving force and the displacement, there is a phase lag or a phase lead, depending on whether you go through the resonance. And actually, in mechanical systems, because of dissipation, there ends up being essentially a phase delay between your force and your displacement, or your stress and your strain. So that's the most general way of thinking about a spring. That's a lossy spring. So then you can say, well, okay, that's the equation of motion for that spring, which is mx double dot plus kx. But all we do now is we're saying that our spring, rather than just being kx, is k1 plus I phi times x. So it's dissipation. This is the dissipative term. And then you can say, well, okay, I'll assume it's a harmonic oscillator. So I've got sort of solutions of the form x equals et I omega t. So if I differentiate dx dt equals I omega et I omega t, which is just I omega times x, and x double dot is I omega times v, or minus omega squared times x, simple harmonic oscillator. And then I take those expressions and I substitute for x double dot and x, so I turn these into velocities. And then the mechanical impedance is just force over velocity. And if that was an electrical system, rather than being a mass on a spring, this would be, for example, a voltage source, an AC voltage source, driving an LCR circuit. And your impedance will be voltage divided by the charge in the system, or the differential of the charge or the current. In a mechanical system, the impedance is a force over velocity. So I've got force, I've got velocity here. So force over velocity is just the expression I omega m, which is this one here, minus I k over omega here, 1 plus I phi. And I've taken the velocity there and I've put it down on the denominator. So that's the impedance. And you can simplify it a little bit more. I'll let you do that, I'll think about that, but all I'm doing there is I'm kind of collecting the terms that are complex and the terms that are in phase. So I get this term here. This starts to look a little bit, you'll recognize this here, for example, omega m minus k over omega. If I divide through by n there, I'll get omega minus k over m omega. So this looks like omega naught squared. So this starts to look like a resonant frequency of my system. So that's my impedance. And then what I can do is I can invert that to get the admittance. So if I want to invert that, I have to at least multiply through by omega. Let me just do that one quickly. So if you've got Z of omega is I omega m minus k over omega plus phi k over omega. Then all we're doing there is we're saying, well, we've got I, and we'll take out our omega, so we end up with an omega squared m minus k plus phi k, and then we can take out our 1 over omega. And then we just invert that, so you end up with omega divided by I omega squared m minus k plus phi k, which is this one here. And that's the admittance. And then, of course, it's usually good to rationalize that, so you make sure that you get rid of the complex bit on the bottom. So you multiply by the complex conjugate, which is phi k minus I omega squared m minus k. So you multiply top and bottom by that, and you just end up with a real part on the bottom, and you get, of course, a real and a complex part on the top. But that's your admittance. And then remember we said in the fluctuation dissipation theorem, we want to work out the displacement noise, which is 4kt over omega squared, the real part of 1 over z, which is the real part of the admittance. We've just worked out the admittance. We just take the real part of it, and the real part of it is just the first term, phi k omega, divided by all of that. So we don't look at that one, because we're just interested in the real part of it. And we do that, we get this expression, and we can simplify this a little bit. We can turn omega naught squared is k over m, so we put an omega naught squared here. So here we've divided through by m, so you get k over m, which is omega naught squared. This, you take an m out here, which is sitting out, or m squared, and then you've got a k over m here, which gives you an omega naught squared up at the top. So dimension, that's correct. You should just convince yourself and check it through, but of course the dimensions of this are all correct, because he's got just dimensions of omega to the 4, and this has got dimensions of omega to the 4. But that's the plot that I showed earlier, where I showed these kind of two plots with different quality factors. Well, essentially the quality factor is held up in the mechanical loss here. So when the mechanical loss goes down, the quality factor goes up. So I can actually now plot out the displacement noise of these oscillators. And I'll do that a little bit later. But that expression there is just the one that's used to plot out that one there. So a high quality factor means a very sharp resonance. So that's what we call Brownian noise. We also have to worry about something called thermoelastic noise. So thermoelastic noise is the fact that you can get temperature fluctuations coupling in through Young's modulus variation in the material, the thermal expansion coefficient. If it's a coating, it might be the refractive index variation with temperature. So these are two types of noise that we have to worry about. But the bottom line is we use ultra-pure materials like fused silica with low mechanical loss. That's one way to provide low thermal noise suspensions. The other way, of course, is low temperature detection. And CAGRA is working with sapphire. And there's also kind of work underway to look at silicon at low temperature. But this is kind of the same slide I just showed. But we've said that thermal energy of KT drives the resonant modes. It's interesting, of course. Here's the plot again. That's the expression we just calculated. If we plot that out for different quality factors, high quality factor is the red one, which means low off resonance thermal noise. So this is a pendulum suspension, and these are the internal modes of the test mass, which are up here. So what you do is high Q materials both for the test mass, both for the suspension, and you get low off resonance thermal noise, and that's your detection band where you operate your instrument. So fused silica is fantastic. It's got, mechanical loss of about 10 to minus 7, which is really good. It's not quite good enough. We need to play another trick, and that's called dissipation dilution, in order to hit the 10 to minus 19 meters per hertz. Now a little bit on suspensions, and we'll pick up your question on local and global control. So these are suspension. This is the quad. The seismic isolation will be attached up here. So we've got 4 stages of isolation. We've got a mass here, a silica mass here, and a silica test mass there. So what we're doing is we're providing isolation. So we've got springs to provide vertical isolation. We've got one stage of springs another stage in here, and 3 stages of vertical isolation, and then you've got 1, 2, 3, 4 stages of horizontal isolation. So we get good seismic isolation, about a factor of 1,000,000 at 10 Hertz. We get thermal noise reduction, so the lower stage being made out of fused silica means we get low thermal noise performance. This is just looking at the suspension, so we've got the test masses here, and we've got attachment points. These are the ears, and these are the fused silica fibres. I'll show you some more pictures in a little bit. We worry about local and global control that we were talking about earlier. We actually have 2 chains. We have the main test mass chain here, and we have what we call the reaction chain. And there's actually magnets on the main test mass on these top stages. So both the reaction chain and the test mass chain have magnets on the top, and these provide local damping of the suspension itself. But then, of course, as you see as you go down, there's magnets on this stage, between these 2 stages, magnets between these 2 stages, and actually on the bottom stage, on the reaction chain, there's a coil. This is a gold coil, actually patterned onto the glass, and this is the test mass of the interferometer. So these red and green magnets, these apply forces between the stages, so you're applying forces between a quiet reaction point, and those apply the global control signals from the interferometer to set the interferometer length. And maybe actually you want to apply electrostatic forces just on the test mass, maybe micronewton levels of force to actually provide maybe some damping of violin modes, of parametric modes that are being rung up by the laser cavity field. So that's the local and the global control of the suspensions, and that's done with magnetic coil actuators. These are a few stages of suspension construction. So here's the mirror here, it's got a protective coating on the front. We have a fibre pulling laser machine, one in Glasgow, there's one in Virgo that we built for our colleagues, and we also built one for the LIGO Hanford and Livingston detectors. So there's 3 machines around the world now. We have lots of profiling, lots of ability to do characterization of the fibres. That's another view of the fibre. So there's a fused silica rod here that gets melted with a carbon dioxide laser, and then this arm here gets pulled out, and that pulls into the long, thin string fibres. They're about 400 microns diameter at the thinnest point, and I'll tell you a little bit about why we make them that diameter. That's a nice picture of a suspension. That's an ear. So here's the ear of the well, this will be the test mass because it's the way it's sort of hanging. Those ears are hydroxy catalysis bonded onto the side of the fused silica optics. So we're looking at that one down there at the bottom right. And then you can see here the ears here. These are the ends of the fibre. This is the stock material. This is 3 millimeters diameter. This fibre here is 800 microns in diameter, and this is also 800 microns. There's 2 fibres on the other side. And you don't see, but actually just out the picture, just about here, that goes to 400 micron diameter. And we do laser welding, so we pull the fibre, and then we offer the fibre up to the ear, and we do laser welding to actually make these joints here. There's a lot of experience of building suspensions both for GEO and also for advanced LIGO. So here the suspension fibres are operating at about 200 megapascal, and there's good reason for choosing that stress because it makes a null in the thermoelastic noise of the suspension that we'll see later. But actually the thinner fibres are needed to provide low frequency bounce mode and also high frequency violin modes, and I'll show you that a little bit later also. These are evolution of suspension. So this is GEO suspension that really kind of Glasgow pioneered the work on the fused silica monolithic suspensions, and then really upscaled that, developing these laser-based fibre pulling machines. And this is one of the final article suspensions that's now in LIGO Hanford. Just at the end, now we're coming to the end of O2. There'll be another round of kind of switching out suspensions in the end chambers. So that's starting probably sort of September time. So there'll be some more installation work that will go out for Glasgow. We provide support for all the suspension installations. These are pictures of suspension. You kind of bolt it onto the bottom of the isolation. You kind of crane the whole thing into the vacuum chamber. So we do this what's called a cartridge installation. A little bit about calculating thermal noise. I think it's important that as well as seeing what we do, you get an idea and appreciation of the noise model. So silica's a fantastic material. Even silica on its own is not quite good enough. So if you took a rod of silica imagine a thick rod of silica, and you said, well, okay, I'll let that oscillate. And that'll oscillate at quite a high frequency because it's a thick rod. Well, we don't make suspension fibres out of thick rods. We make them out of really thin fibres. And you might say, well, why do you do that? And the reason we do that is we get another factor of sort of reduction in thermal noise called dilution. So if you make a suspension fibre thin, so here you've got the end of the fibre, 3 millimetres, goes down to 800 microns here and then down to 400 microns in the thin section. If you make a thin suspension fibre and you push it sideways, then actually what a pendulum does is it actually wants to lift in the gravitational field. So if I take a single pendulum and I push it and I say, okay, there's my starting point, then what happens is I push it to the side. Well, actually it kind of goes in a parabolic path. So what we get is something that looks like that. So we've actually lifted up in the gravitational field. And of course you can work that out and you can say, well, what's the angle of this? And it will be a cosine theta times the length. So we've lifted the suspension up in the gravitational field. So we stored some of the energy, not just in elasticity. So elasticity, we store the energy in the bending point of the fibre. But we've actually stored some of the energy in gravity. Now, of course, we don't use 2 single fibres. We use 4 fibres. So actually 4 fibre suspension. It does the same type of thing, but it does what's called a parallel transport. So when we push the suspension to the side, what it does is the fibres go into this, it's an awful drawing, but it goes into this S shape. That is an awful drawing. Let me do that again. Because that's a fibre under tension. So what we get is we get a bend here, and then it's that's much better. So you get a bending point there, and there, and there, and there. And here you just get a bending point here. But bottom line is we've lifted that mass in the gravitational field by a vertical height h. And the gravitational field's conservative. So what we do is we store some of that energy of the suspension in gravity, and a little bit stored in elasticity because we have to bend the material. But it's not as much as if you make it out of a thick rod. If you make it out of a thick rod, all the energy is in elasticity, and you see the full mechanical loss of the suspension. The trick you play with dilution is that if you suspend some of your you put some of your energy in gravity and some of it in elasticity. If you put all of it in gravity and none of it in elasticity, you don't see the thermal noise of the material. Of course, you have a little bit of bending there. So what we do is we get to dilute the mechanical loss of the suspension fibre by the ratio of the gravitational energy to the elastic energy. And that's why we make fibres thin, because when we make fibres thin, we store more energy in gravity, less in the elasticity of the material. So I won't go through this, but essentially what we're doing is there's this dilution factor, which is the ratio of it's kind of the total energy divided by the elastic energy. And that's pretty much dominated by gravity, the total energy, divided by the energy stored in the fibre. And if you kind of work that out, then it depends on the kind of tension in the fibre, the material properties like the Young's modulus and the second moment of area, and the length of the fibre, and this parameter here called eta, or zeta, or whatever. And actually this is 1 when you've just got a pendulum that's got 1 bending point, and it's 2 when you've got a 4 fibre suspension like LIGO, because you've got 2 bending points. So you get a little bit worse dilution when you've got 2 bending points, because you've got bending both top and bottom. But even so, for advanced LIGO, that's about a factor of 100, 90 or so. So it means you can take the 10 to minus 7 and reduce it by a factor of 90, which gets you to 10 to minus 9. And that's what you need to get 10 to minus 19 meters per hertz. We'll do another few minutes, then we'll have a break, because that will be an hour then. Fused silica is a remarkable material. This is kind of the breaking stress versus fibre diameter. And actually you can see it's pretty flat. Out here is because fibres break not just in the pristine thin section, but at the ends. But the strength of these fibres are about 4 to 5 gigapascal. And these fibres are, they're elastic, but unlike metal, they don't creep. So you pull them and you stretch them, and then if you take the load off, they go back to their initial point, even when you stress them up to 2 or 3 gigapascal. And a metal will just start to plastically deform. They will undergo, of course, when they break, an explosive fracture, as you see here. This was done with a flash gun. But actually, this stress here is about 4 to 5 gigapascal. Remember, we said that the thin section of fibre is operating at about 800 megapascal. So it's about a factor of 7 under the safety limits. So that allows us actually, there's a bit of more room to actually make fibres even thinner, and that's one of the things we'd like to do, pushing forward suspension upgrades. You can calculate this. It's nice to calculate, what does the fibre undergo when you put it under full load. Well, Young's modulus is just stress over strain. And you've got 4 suspension fibres. Each fibre is carrying 10 kilograms of mass. So you can say, well, what's the stress in a fibre? And for the 400 micron diameter section, which is 60 centimetres long, then the stress, well, the length doesn't matter, of course, but the stress is just 10 times G over pi times, that should be 200 microns squared, but that gives you 780. That would be in the thick section, which will give you 200 megapascal. So it's about 800 megapascal in the thin section. And you can say, well, how much does that suspension fibre stretch under load? And then you can work out the extension, which is strain times the length, which is sigma over y times the length. So when you hang the load on that fused silica suspension, it stretches by 6 millimeters. So over 60 centimeters, it stretches by 6 millimeters. So that's an so in terms of a strain, it's about 1% at that point. But it's still a factor of 7 under the ultimate kind of tensile strength of silica. We do lots of tests to understand the breaking of fibres. So we do sort of high-speed imaging. I won't show the video. I can show you later if you want. But you do breaking of fibres under high stress, and you see explosive fracture. You can understand where fibres are breaking, and really strong fibres always break in the pristine section, and that can be up 4 to 5 gigapascal. So we operate comfortably with a factor of about 7 under the ultimate tensile strength. A little bit about geometry again. So we talked about this kind of dilution. Now you can do that analytically, and that's the analytical expression again for dilution. Really what we do, remember we showed earlier some pictures and we said, well, we do we predict the profile and the geometry of the fibre. So we actually look at the diameter of the fibre as a function of its length. And we do that so we can actually predict the thermal noise performance and actually analytically predict the dilution. Because what makes the big difference is the attachment points of the fibres. So these fibres don't kind of transition from a flexible material to something infinitely rigid. They've got a neck on them. So the fibres have a neck of 3 millimeters, and although that's pretty stiff compared to the thin section of the fibre, it's not infinitely stiff, so we have to worry about those attachment points. So we do finite element analysis, and we can predict for example, the analytical dilution for a particular cylindrical section would be 112. This is a ratio, of course, gravitational energy to elastic energy. But actually, if you do FEA on it for a typical fibre, it's a little bit lower than you expect because there's a bit of bending going on in the thick section of the fibre. What we're saying is that energy is not all just constrained to where the bending's going on, but it actually leaks up the end into the kind of thick section of the fibre. So it's very important to actually do finite element analysis, do the optical profiling to actually measure the geometry of the fibre and actually feed those real fibres back into the suspension thermal noise model. Last slide, and then we'll have a break for a few minutes. So, for example, with our fibre stock of 3 millimeters, this is the end of the fibre that we saw in the photo, and then we go through the neck. This is the 800 micron section. Here the fibre stress is about 200 megapascal. And then we go down to 400 micron section, which is shown over here for the majority of the fibre. And the thin section is such that the bounce mode of the suspension should be under 10 hertz, so it's about 9 hertz. But we also want the violin modes, which are the kind of longitudinal vibrations. So these are a little bit like guitar strings. They're fused silica fibres under tension. So we want those above well, the requirement's about 450 hertz, so we get them above 500 hertz by making the fibres 400 micron in their thinnest section. There is a good reason for making this fibre 800 microns at this end section, and this is where all the bending occurs. So we'll have a break. Let's do it 5 minutes, and then we'll come back. Right, I think we'll start again in a few minutes. We've got lots to get through, so what we were doing, we were talking about the fibres. So that's what the fibres look like. In terms of a noise model, I mean, maybe there's a little bit too much detail, but at least you'll get to see it. So we have to worry about multiple noise sources. So when we look at kind of fibres, the dominant two are this one at the bottom. So this is what we call surface loss, and it's the fact that a fibre has a surface, and that surface has a dissipation associated with it, partly due to maybe damage to the surface, dangling bonds. So when you actually look at different fibres of varying diameters, you see a surface loss that actually correlates with 1 over the diameter. So it's related to the ratio of the surface area to the volume of the fibre. And then the other one that's important, remember we talked about thermoelastic, so this is one where thermal fluctuations can couple into mechanical properties of materials. So this one, for example, will be coupling through the thermal expansion coefficient for suspension fibres, and the other one that is kind of held in here, this beta is a variation in the Young's modulus with temperature. So it's actually 1 over y dy dt. So it's per Kelvin, just like the thermal expansion coefficient. And that's thermoelastic loss. And that would be very important in these suspensions, except that we choose the diameter of the fibres very carefully at the ends. And when we do the full finite element analysis, what we do is we take each section of the fibre and we look at the individual loss terms. There's a loss term also due to the fact that we've welded the material, we've heated up the glass. We take all of these different loss terms, we scale them by the different energies in the fibre, and we kind of sum those all up to generate the total thermal noise of the fibre. And actually doing the analytical expression, you get very close to the expression you expect if you use the analytical expression of the dilution factor. So there's a real neat property of fused silica. It's a fantastic material. I mean, it breaks, the ultimate tensile strength is 4 to 5 gigapascal. Its other really interesting property, unlike all the metals, is its Young's modulus increases with temperature. So it gets stiffer with temperature, whereas all metals get softer with temperature. And that has a really interesting property in terms of its thermal expansion coefficient. So it means you can make a fibre that's got 0 thermal expansion coefficient out of fused silica just by choosing the geometry of the fibre alone. And these are some experiments that we did in Glasgow. Myself, Stuart, we did them together. So these were experiments. Here what you're doing is you're changing the temperature of a fibre. So this is hot, cold, hot, cold, hot, cold. And this is the extension of the fibre. Gets longer, gets shorter, gets longer, gets shorter. The thing to point out, you won't see the numbers, but just look at the kind of when you increase the temperature, the fibre gets longer. So this is in phase. And then the one down here is again hot, cold, hot, cold. It's about 40 degrees different. And this is the extension of the fibre, longer, shorter, longer, shorter. The interesting thing now is the phase has changed. So before these two were in phase, now these are out of phase. So what it's telling you is because of this Young's modulus property of the silica fibres, if you take a lightly loaded fibre and you heat it, it gets longer, just due to the alpha, the thermal expansion coefficient. If you put lots of load on the end of that fibre, so you get the Young's modulus becoming a dominant factor, and you warm that fibre up, it shrinks. And that's why you see this phase change. The fibre is actually getting shorter when you heat it up. And that means there is a certain stress in there where you can make no thermal expansion coefficient, and that's how we operate our suspensions. We operate them such that when we change the temperature, we get no change in the kind of length of the fibre. And that's by tuning the thermal expansion coefficient to the Young's modulus, and that occurs at about 200 megapascals, which is a thin, that thicker section of the fibre, the 800 micron part. And if we do that at 10 hertz, thermoelastic sits down here, and we're dominated now by surface loss and the weld loss of the fibre. So it's really neat. A little bit on violin modes. I mean, these are remarkably low thermal noise suspension systems. This is results from our early prototype in Lasti. This shows you the ring down of a suspension, a violin mode resonance of the suspension fibre. This is in hours, so this is over 20 hours, and we're going from about 10 to about 7. So 1 over E would be the quality factor. So we're looking to go from about a factor of 33% variation. So this is not even 1 over E, and that's almost a day already. This is a Q of about 300 million. The quality factors of the suspension systems now in the LIGO detectors are up around between 700 million and 1 billion. And again, you can calculate this. I'll leave this for an exercise for yourself, but the violin mode frequency, essentially the violin mode frequencies, this is under tension. So this vibrates backwards and forwards at a certain frequency. That's what we call the violin mode. just like it's a guitar string. So you've got mass per unit length, which is the rate, is the square root of the tension over the mass per unit length. That's the speed of the wave along the fibre, which actually for these fibres, which is 400 micron diameter, it's about 600 meters per second. And that gives you a frequency of about 496 hertz for the lowest order mode. We measure about 500 to 510. And then if you look at the quality factor for 300 million, pi times the number of oscillations to drop to 1 over E, the time it takes to drop to 1 over E is about 2.7 days. So when we see these Qs of about 1 billion now, it's taking about 10 days to drop to 1 over E after you get a thermal excitation. Extremely low mechanical, very low mechanical loss, ultra low thermal noise. These are useful equations. This is kind of captures together all the bits and pieces we've been talking about. Fluctuation dissipation theorem, the quality factor, the dissipation dilution, the loss terms. These are the pendulum mode frequency, the bounce mode frequency. This is a mass on a spring. The Young's modulus as a stress over strain, the extension of the fibre. You can put all that into an analytical model, and I've done that for you. I'm happy to share it with you. I did that last night. I thought, let's build up a suspension model. This is just in an Excel spreadsheet. So you've got all the properties here, like the mass, the length, the thickness of the thin section, the area of the fibre, the stress in the fibre, the tension, the temperature, the tension in the fibre, the specific heat, the thermal conductivity, alpha, the Young's modulus variation with temperature, the density. And what you do is you can work out all the properties of the suspension. So it'll be a wee bit small to see, but the pendulum mode is 0.6 hertz, the bounce mode is 9 hertz, the first violin mode is 496 hertz, we've just calculated. Dilution is about 100, but smaller for the analytic, the FEA expression. The speed of the wave, the violin mode is 595 meters per second, and you can put that and work out the thermal noise for the vertical and the pendulum. And even this analytical model, at 10 hertz, the total thermal noise is sitting at about 10 to minus 19 meters per root hertz. And using just those analytical equations, you can start to see how you can build suspensions of this required level. So I'll happily share that with you, but that's your equation toolbox to calculate the properties of your suspension. I'll just spend a few minutes just talking very briefly about future developments, upgrades, and then we'll switch to the other topic that Christian had asked me to talk about. Again, when you're looking at the detector noise, this is your thermal noise here. So at 10 hertz, now of course we switched to strain, but it's about 5 times 10 to minus 23. So one mirror is 10 to minus 19. There's 4 mirrors. If they're all kind of at in quadrature, then the strain noise is 2 times 10 to minus 19 divided by 4,000. So it's 10 to minus 19 over 2,000, which is 10 to minus 22 over 2, which is 5 times 10 to minus 23, which is sitting here. So that's 10 to minus 19 meters per hertz at 10 hertz. We're doing lots of other work on suspensions. We're looking at thin fibre work. So this is for work in Glasgow on a speed meter experiment, but we're also working with the Albert Einstein Institute to develop 100-gram suspensions. So these are operating with, this is the end of a midsection of a LIGO fibre. This is 400 microns, that's our stock material, and then we pull down to 10 micron fibres. So we're doing the techniques to, these are the ears of our suspension, at 10 millimeters by 1 millimeter across, really tiny things. These are our springs for passive isolation. So some really nice work ongoing there. We're doing heavy suspensions. So we're working up to future upgrades. So for example, can you suspend 160 kilograms rather than 40 kilograms? So here's a single 40 kilogram optic sitting on a long, slightly thicker fibre, operating at a little bit higher stress. That's been hanging since December. We have a system out in Hanford that's been hanging for over 2 years now at about 1 gigapascal. So these are all what's required in order to prove the technology for future upgrades. Because thinner fibres mean your dilution is better, longer suspensions mean your thermal noise is better. These are ways to get factors of 2 and 3 improvements. In terms of, we talked about thermodynamics and you're battling against KT, of course going to lower temperature. So for example, cryogenic operation. So we're working on development, in Cadwell is sapphire suspensions. Also, LIGO, Voyager and Einstein telescope, they're interested in looking at silicon suspensions. So we are developing growth machines to produce crystalline materials. So for example, this is a machine that we're building up in Glasgow to grow crystalline sapphire and ultimately silicon. This is a CAGRA payload, a 23 kilogram sapphire mass that's a prototype payload that's recently been installed, so that's excellent progress ongoing. But the performance of cryogenic really give you the sort of order of magnitude improvement in low frequency performance. You have to say where do you operate, what's your temperature of operation. Around 120 is an interesting point because silicon's got a null external expansion, so this minimises thermoelastic loss. And you can do radiative cooling, whereas actually looking at CAGRA, they're going to sort of 20 Kelvin or less than 50 Kelvin, and silicon has another zero in its thermal expansion coefficient at about 18. Sapphire has very good performance at low temperature. But of course, there's more stringent requirements in terms of the cooling and how you extract heat out of the optic at those low temperatures. So these are the things that we're thinking about in the next round of third generation detectors. So that's the first lecture finished. I can take questions now or can take questions at the end. Otherwise I shall switch on to my other topic, which I've been asked to talk about, which is precision measurements. Are there any questions? Otherwise I can hold them to the end. Okay, let me continue. So I was also asked to talk about kind of spin-off technologies, and I work on MEMS gravity sensors. So actually this is the Excel spreadsheet there, so I'm happy to share that with you. So this work is kind of something that's been developing over the last 4 years. So here we're taking kind of the technology from the gravitational wave side in developing suspensions and building precision optomechanical systems which have applications in gravity surveying. So kind of overview. This is work done under what's called the quantum technology hubs in the UK. I'll show you very briefly what the quantum technology hubs are, and then I really want to spend most of the time talking about the device because that's where the interesting thing is in developing high precision gravity sensors, using some of the tricks in suspension technology and some of the modelling techniques that we require. So the quantum technology hubs. So the UK government about sort of 2.5, 3 years, almost 3 years ago now, they put in about £270 million. Across 4 quantum technology hubs in the UK. One of those is led out of Glasgow, and it's called Quantic, which is a quantum imaging centre. It's kind of led around 4 work packages, so 3 work packages of development and 1 in terms of components. So things like imaging with correlation. So for example, things like using single pixel detectors to actually develop full image scenes. So can you make an image out of a single pixel? You can if you put something in front of it, like a coded mask, that you change the coded mask, and you know what the mask pattern is, you can change the coding and to extract the image. And that's very interesting when your single pixel is quite expensive, like for example a shortwave infrared detector. We can do imaging with timing. That's another activity that's led out of Heriot-Watt. So that's looking at accurate timing on silicon pixels and single photon sensing devices. There's another work package where our work on the MEMS is sort of sitting, and that's imaging with squeezing. So here squeezing, of course, just like in the gravitational wave sense, is we can decide to reduce the, for example, the shock noise of an interferometer by squeezing the phase quadrature. Of course, at the expense of making the noise worse at the low frequency in terms of the amplitude quadrature. So LIGO, of course, would eventually implement frequency-dependent squeezing, where you squeeze as a function of frequency. But we're sitting, because we're looking at optical readout systems, we're building MEMS optical sensors, and ultimately those could incorporate squeezed light sources. And then the 4th work package is on componentry, and that's kind of done out of the James Watt Nanofabrication Centre, which builds laser sources, packaging sources, works together with Strathclyde building LEDs, optical sensors, germanium on silicon, single photon avalanche diodes, all kinds of the things that underpin these different scientific work packages. This is kind of a busy slide, but where we typically sit in terms of underpinning fundamental science would be on the left-hand side. The quantum technology hubs kind of span this region between fundamental discovery and engagement with industry. So here's all the industries here that would like all the technology to come from here. But of course, it's quite hard to take and translate that technology, and the quantum hubs are really there to do that. So while we're developing on our side, we're developing these MEMS sensors to do gravitational imaging, we have a very clear focus on developing the device as a potential future product. Why would you want to image gravity? And what are the challenges to date? Well, actually, there's a number of reasons. Oil and gas prospecting, well, they use seismic sensors. We talked about seismic noise. So seismic sensors are pretty much the standard for looking at kind of oil fields and resource management. But actually, even before you go down and do a seismic survey, you probably fly over the region first, because you don't always want to get onto the ground where you're going to drill your well until you know there's something on the ground that's of interest. So in the oil and gas industry, there's a huge push in better sensing, more sensors, array-based sensors, because actually when you drill a well and you want to make sure you get sort of maximal resource extraction, and if you have only a single gravity sensor that's measuring how much oil is in the ground, then that can be a significant limitation. So actually array-based sensing is a real interest for the oil and gas industry. If you put stuff under the ground, environmental monitoring, gravity gives you a way of knowing 10 years later, is it still where you think it is? Because you're looking at the gravitational signature of what you've put down there. High speed to rail, it's an interesting one, because you need to keep, these trains are moving at such a high speed, you need to keep the track level to, I think it's like 2 to 5 millimeters. So that means you need to know what's under the ground, and you need to drive piles into the ground. So having good seismic and gravity monitoring for really the civil engineering is important. Security and defence, there's a number of tunnels that are being sort of dug in different places around the world, and you can use microphones if you're listening for a tunnel being dug, but you might want to know at borders of entry, is there something under the ground? Volcanology, so precursor to sort of magma extrusion from a volcano, can be actually the caldera filling up with magma, and that's even before the ground starts to tilt. And you can see you get an early warning system for volcanic eruption from the gravity signal. And then of course civil engineering, more and more houses are being built on brownfield sites, and actually I can see in the next 10 years that a standard tool, as well as your pollutants, do you live on a floodplain, will be, do you live in an area where there could be mine shafts, or it will be more, do you live in an area where there are mine shafts, because houses and roads sometimes disappear into them. So if you live in Florida, that's not a good place to live. What's the kind of instrument space? I mean, I think the important thing is when you're looking at new technologies, where do you want to fit in? So there are kind of state-of-the-art standard instruments, and they're sitting out here. They're kind of big, so the standard, what's called an absolute gravimeter, it takes a mass and it drops it, and it just measures the acceleration. So it measures a little g directly, it's an absolute meter. So these are state-of-the-art, but they cost £250,000, and they're kind of 150 to 200 kilos. They're not portable instruments. Your portable instrument is a relative gravimeter. It costs about 60 to 70,000 pounds. Pretty expensive. Means that a volcanologist can only have one of them when they would like 10 to 20. So that either requires that you have to get together with another 10 other volcanologists, or you have to take that meter and you have to carry it around the volcano. And if you see videos of volcanoes erupting, you don't want to be doing that. It's really a dangerous thing to do. So array-based sensing is really important there. But they cost, there's still tens of, can be 10 kilos. Although they are portable, there's a system there. Then you get these devices. These are sort of inertial accelerometers. These measure inertial accelerations, seismic waves emanating across the table or across the ground. But they don't measure gravitational acceleration. And then your Android phone or your iPhone, it tells you whether 1g is up or down, so it can rotate the screen, but it can't tell you much else, so it's about a milli-g or so. So we're trying to build these devices that are maybe 3 or 4 orders of magnitude more sensitive than your iPhone, but are similar sensitive, similar size, and cheaper. kind of, why do you build a certain device? Well, what we did about 4 years ago, we looked and we said, well, we want to measure a certain acceleration. And the acceleration we want to measure is what we call 300 microgal. In terms of SIE, that's 300 nano-G, 300 billionths of a G, where 1 G is 10 meters per second squared, and if you want to do that with a few nanometer displacement, it kind of tells you the resonant frequency of the device. It's a mass on a spring. It's a suspension system of a gravitational wave detector. And it means that you need quite a low resonant frequency device, much lower than any MEMS device that have been built to date. So in your phone, they're typically a kilohertz resonant frequency. So what do you do? Well, you can actually make these kind of what we call serpentine springs, where the flexion just goes backwards and forwards many, many times. And that's a device that's made from Imperial College. It's about 10 hertz. We wanted to make one that was about 2 hertz, so you can't really do that with such a device. So we went to the gravitational wave side, where they use these things called geometric anti-springs. These are used in Vertigo, and they're also used in the Albert Einstein Institute 10-meter prototype. And they're essentially constrained springs. You take a spring and you constrain it into the center to move along the center point. And that generates a negative spring constant that softens your spring. So it's no longer a linear Hooke's law spring, but it's a spring that gets lower frequencies. You pull it down more and more. So we kind of did some modeling using our same tools of gravitational wave suspensions. So we started modeling 4 Fletcher devices, and then we modeled, well, we actually broke a device, and it turned out it worked much better with a 4 Fletcher device. So these devices here, they're unstable, so they get softer and softer and they collapse on themselves. This one gets softer and softer, and then it recovers. So this was a real sort of neat find, actually. We probably wouldn't have modeled this to start with. But what we're doing, so the top one there is a 4 Fletcher device, and this is displacement versus force. So of course, the stiffness is dF dz, which is sort of 1 over the gradient of this line. So when of course this goes very steep, it means the thing's getting very soft. And what happens is it goes up here and it just collapses. This gets softer and softer and collapses. Whereas actually the 3 Fletcher, which is this one, it gets softer and softer, and then it recovers and it gets stiffer again. So what you can do with a MEMS device, you can make a proof mass of about 0.02 milligrams, but you can have it with a resonant frequency of 1 hertz, or 2 hertz if you like. So it's a real neat low frequency oscillator. That's the device there, that's the proof mass. You can't see the Fletchers, they're about 7 microns in thickness. That's an SEM of the etching. This is all etched in Glasgow, James Watt Nanofabrication Centre. We have on-chip thermal control we're developing. So these are 4-terminal heaters. This is so a thermometer. This is a 2-point heater. This is a nichrome heater and a platinum thermometer. And we put heaters on different parts of the Fletcher. So that allows us to control the temperature. Because just remember, with the suspensions, we were worried about Young's modulus variation in the silica. Here we worry about Young's modulus variation in the silicon. So it's a direct kind of, it's very complementary. You're building precision up to, mechanical systems on the MEMS side. It's the same kind of things you're worrying about on the suspension side. It's a real nice kind of parallel translation of activity. We worry about the kind of stress in the system, so we do lots of finite element modeling. So we do the modeling of these geometric anti-springs. So we have some really nice tools to model these systems now. And the bottom line is that we can make these resonant systems to be stable at any angle we want. So as we kind of tip them up from horizontal to vertical, you can make them so at 90 degrees is the device is operating vertical. And vertical gravity is the one you usually want to measure, GZ. That's 9.81 usually. It varies a little bit every day. And here you can make one at 90 degrees with a certain resonant frequency. If you change the mass of the proof mass, you get this sort of double minima, one at 80 degrees, and then it gets another one kind of stable on the other side of that, which is about 100 degrees, so 90 is the vertical. And then you can make one here at 66 degrees, and it'll have another sort of minimum over here, 55 degrees, 45 degrees. You can actually make these devices low frequency at any angle you want, which is really interesting if you want to build triaxis sensors. So at some point we'd like to build these into 3-axis sensors. And then you'd operate at about 50 to 60 degrees. And then you'd measure component to GZ, but you'd also measure GX or GY. So you start to access the full the gravitational field in all directions. Because if you've got a very heavy object that side, little g is not pointing down anymore, but it's pointing a little bit towards that heavy object. So that's the device. So We like, of course, fused silica is a fantastic material for silica suspensions. We also use it in our device at the moment as a sort of stable base plate. There's a silicon MEMS. We have a readout, an optomechanical readout. It's a really simple readout. It's just an LED, and the proof mask casts a shadow onto a photodetector. So it's what we call a shadow sensor. They're used all the time in the LIGO suspensions. Remember when we talked about local and global control, those magnet coil actuators, those have flags on them, and we do the same kind of shadow sensing. The only thing is that shadow sensors for the quad suspension, they only have to work at a few hertz. These devices that we build have to be stable over days time scales, and that's the real challenge, is making these devices such that they're nanometer level or a few nanometer precision, but over 4 to 5 days. That's the real challenge here. Because there's lots of things that will actually change your output as a function of time. So we modulate. So actually in LIGO they don't modulate, because in LIGO for suspensions we worry about any modulation, because any modulation could couple into the kind of output of the interferometer. But here we modulate. So we modulate with a kind of pseudo sine wave. So we go high, 0, low, 0, high, 0, low. So we modulate, and that allows you to do a quadrature photo detection as well as in phase. So you can get 0 and 90 degree phase. We get a shadow here, so the shadows cast over these two photodiodes, and as the proof mass goes up or down, then we see more shadow on photodiode A or B. You put that through a good transient impedance amplifier, you demodulate it with a lock-in, you filter, and then you log the data. Fairly standard way of operating. Of course, the challenge is how do you make that such that it's stable over daytime scales at the level of a few nanometers. That's the tricky thing, because there's a lot of stuff out there that will stop you doing that. Things like LEDs are, the beam wobbles, and you can't tell the difference between the beam wobbling and actual motion of the proof mass. Because the proof mass is moving due to both inertial accelerations of ground motion, but also because little g is changing twice a day. Remember we talked about the tides? So little g is changing, so that proof mass is going up and down by a few nanometers. And our goal was to measure the earth tides, because when you measure the earth tides, you've really got a device that can measure gravity. So LEDs can also change colour. They can, the full width half maximum of the intensity can change. You can infer all of these things can look like a displacement variation. In the silicon, there's thermal expansion, there's temperature variation of the Young's modulus, temperature variation of the electronics. These are all the things we have to kind of battle against every day in gravitational wave detectors, but also the MEMS side. But anyway, we put it all together. We had money from the Royal Society Paul Instrument Fund to actually build a device demonstrator, and we actually use that demonstrator. So the red is actually the theoretical prediction of what we call the earth tides, and these are changes in little g, typically twice a day. Sometimes they're once a day, depending on the phase. So here's a once a day, and then you see the twice a day diurnal tides growing as well. You can see the diurnal tides here. The reds are the theoretical, of course. The blue is the messy one, which is the real data. But actually you can see that there's a very good correlation of the earth tide signal with the actual measurement signal. And that's not kind of fitted, that really is calibrated as we measure the output of the device. And then you do a lot of filtering, and you can actually see there's good correlation. These variations here are due to intensity fluctuations in the LED. But it showed that the device worked, and that's important. And then we did some more measurements, so you can see here you get the diurnal tides twice a day, and then you get the single once a day but large tides, and then you get the diurnal tides. This is when, of course, the moon and sun are kind of like this, or at 90 degrees to one another. You get the twice a day or once a day. And then you can filter the data, so you see some reasonable tide data. That's probably really nice data over part of a day, and you really see, actually you can see the diurnal peaks here, and this one here. Anyway, the device was working, so that allowed us then to, we got onto the Quantum Technology Hub, as well as being a really nice, what we call a gravimeter. So this is an accelerometer, but it measures gravity, gravitational acceleration, so it's a gravimeter. It also is a pretty good inertial seismic sensor as well. So we usually operate just down here, the earth tide. So this is 10 microhertz. That's one day, 10 microhertz. This is the resonance of the device, 2.2 hertz. This is a microseismic peak, so we see seismic noise really easily. And that actually seismic noise actually drives the resonance of the device. So here's the microseismic peak that we talked about. And it's a double peak actually where we are, because you see both the Atlantic and the North Sea. And that varies as a function of time. That's an artifact, that's just our thermal servo. So it's actually pretty white out here in RMS. And then you see the peak here, that's the Earth tide peak. So it's a sort of 5 orders of magnitude wide bandwidth seismometer at high frequency and gravimeter at low frequency. And then what we were doing over the last year is really miniaturizing the system, because remember the Quantum Hub is about getting the device out into the hands of industry. And the Earth tide was done in that kind of lab where there's rack-mounted electronics, and we want to get this into a small kind of vacuum system with running off portable electronics, battery-powered electronics. I could talk to you plenty about that if you want, but essentially it's all run off a digital signal processor. That does the digital modulation and demodulation. There's temperature sensors, heater control, all the kind of stuff you need to actually run these systems, but off 12-volt batteries, or ultimately lithium-ion batteries. So this allows us to run autonomously in the field now. You can log data, you can also take its GPS location. It's pretty good. I mean, over a couple of days, it holds the temperature to a millikelvin. And actually the noise, the white noise, is at the level of about 10 nanoG, which is perfectly good for what we need to start with. We've done some trials, so we have got the device out into the field. This was only a few months ago. So there's various things you can do actually when you're testing it. It's pretty hard to generate the tide signal. If you say, I want to generate 300 nanoG, that's pretty tough to do in the lab. A person at 1 meter is 1 nanoG. So it needs to be 300 times bigger than that. So you've got to get a lot of mass very close, and it actually becomes impossible to generate a tide signal. So you say, well, how can I do that? Well, actually, the thing you can do is you can take your device from the floor, and you can sort of lift it up by 1 meter, because what am I doing now? I'm moving away from the center of the Earth. And as I move away from the center of the Earth, I'm reducing little g. So what I'm doing is, if I'm at the center, I'm sort of looking with my device here, then little g is, assuming the Earth is spherical, is gm over r squared. That's little g. It's the integral of the mass under your feet. That's what little g is. So of course, if there's a hole under your feet, then little g is not quite the global value, and that's why it's very interesting to measure gravity at the kind of few tens of nanoG. But if I lift this device and I say, well, what's dg by dr, the gradient, then that's just, well, the modulus of that is 2gm over r cubed, which is 2g over the radius of the Earth. If you work that out, it's about 300 nanoG per meter. So if I move up 1 meter, that's 300 nanoG. That's the Earth tide signal. So that's a really easy thing to do, except that you're moving the system. So you're moving this incredibly delicate system. So here we go to the elevator, and we go. It's the other way around. So this is actually, although this is high. This was bottom of the building, top of the building, bottom of the building, top of the building, bottom of the building. And you're seeing a 6 milli-G signal, and that's due to the fact you're going up about 17 meters. And then we did the other thing, which kind of you need to do when you get your device out, is you take it up a hill. And this is an interesting one. So the one on the right is taking, as you see, we're outside. So that's the device operating outside a car, up on the top of our local hills. It's about a 200 meter elevation. And that's really hard because now temperatures are varying quite a lot. So the interesting thing here is you take up a hill and you get this kind of changing gravity just due to the height, and you say, well, I've gone up 200 meters, so therefore gravity's got weaker. And it has indeed, and that's actually the red line here, which you can't see very well, but I'll point it out. This is the red line. That's the line you'd expect just from what we call the free air correction. And then the other red line is down there. It was a 2-stage measurement, so that's halfway up, that's all the way up. And it's not along the red line. So you might say, oh, gravity's not what we expect. But actually what you have to be aware of is this is what we call the free air correction. But actually when you're up on the side of a hill or a mountain, you're now sitting on all this rock underneath. And that's pulling you down a little bit. So this is what we call the Boyer anomaly. And that's the green one. So when we actually take account of the fact that we're now on the side of a hill, then we actually do sit reasonably well aligned with where we'd expect to be for, that's assuming granite, and it's not quite a granite hill. So we've actually got the device out, it's measuring vertical gravity. What are we doing now? Let me tell you a little bit about some of the projects that we are ongoing, and then we'll just wrap up just at the end. So this is working, actually you might have, Andreas, there's Andreas, I will not point at you with a laser, but so you might have talked to Andreas during the week. So Andreas is working on this project. So this is together with a large multinational called Schlumberger, and they make seismic sensors. They do downhole technology. So we're building on-chip Michelson interferometers with them, together with them. So, you know, of course, interferometric sensing, we're working at the moment with our shadow sensor at, you know, it does a couple of nanometers over 10 seconds. It does a couple of nanometers over 5 days, which is pretty good in terms of long-term stability, but we'd really like to get to, you know, picometer sensitivity, which of course interferometric sensors allow you. So we're doing sort of small on-chip interferometers where this will be about, you know, a few millimeters across. One of these will, you know, here's the input fiber with the ball lens for collimation. This goes off to our MEMS device here. This is a reference mirror. And then this is a photodetector. This will eventually be a piece of germanium on silicon. So we're integrating photodetectors, but we can start off by kind of pulling the beam off the chip. We're doing a lot of work. So Andreas has an interferometer set up on the bench where we're just sort of locking it to the mid fringe. So we see a lot of sort of direct power noise coupling in because we're just sitting high sensitivity point. And there's a lot of sort of acoustical coupling, a lot of air coupling. But even still, at 1 hertz, we're getting down to a few 10 picometers or so, which is much better than our shadow sensor. So we're kind of working on this to improve this over the next months or so. This is still a large system, so this is still on a breadboard, and we're just at the point now of making these devices in the James Watt Nanofabrication Center, so we can actually start to integrate the on-chip devices, and I expect a lot of those couplings will go down because we put the system in vacuum, and then we'll have to probably compete with just direct laser noise coupling. We're doing some work on underwater gravimetry. I'll not exactly tell you why, you can probably guess, but you might want to detect things under the water. This is working with a defence contractor called Kinetic in the UK. And it's a kind of part modelling project, part experimental project. So we're just modelling, gravitational signatures. Well, I'll tell you what it's there for. They've seen this slide, so they're very happy with it. But you might want to look at ports of entry. So submarines are interesting because they're nominally neutrally buoyant. So far away you don't see them because their monopole moment is 0. But they have high order moments, they have gradients because there's heavy bits and there's light bits. So what we're doing is we're predicting the gravitational signatures from these devices, and this is the total magnitude of gravity. This is kind of the X component, which is just a component directly towards the device. And you kind of see this interesting behavior where the gravity goes down a little bit to start with. If you look at it come back, the gravity goes down and then it goes up. And that's telling you there's a light bit at the front, a heavy bit in the middle, and a light bit at the end. It's neutrally buoyant, but it's got gradients. So we'll start to do some modelling of that, some further modelling. This is a great opportunity for match filtering. You see this all the time in gravitational wave detection, where you've got a certain signal you want to look for, and in our case it might be a certain mass signature that we want to actually hunt for in the data. So I think this is going to be an interesting sort of ongoing development, and ultimately we'll actually get some packaged devices and actually put them under water. The other one we're working on is with a survey company called Bridgeport. They work down in Milton Keynes. And the one we're doing there is actually a side-by-side test of our gravimeter, so our MEMS gravimeter together with a commercial gravimeter, which is going to be an interesting one. I think getting out to the field early is good because you realise what doesn't work and what does work. This is Kröken around 1958, I think, and you can see the differences. There's just a valley here. And this is sort of in the 60s where they actually kind of put a reservoir. So they actually sort of dammed up the front wall here. So this has now become a pump storage station. So this can actually restart the grid in a blackout. So they always keep a certain amount of water in the upper reservoir because that's gravitational potential energy. And usually what happens with Kurokan is that when everyone goes to turn on their kettle at the kind of end of whatever the Olympics or the football match or your favourite soap opera, there's usually a spike in the grid. So the generating, the Kurokan typically sort of starts up to provide that peak power demand. And it empties the reservoir typically by a few meters. And the question is, can you see the gravity signal? So we did a little bit of work on digital terrain modelling. I'm sure this play actually. So here you can see, for example, this is the these are sort of topographic maps, and sort of superimposed is the MATLAB signature. So what we did was we did a digital terrain model, and then we worked out the total value of G at different points around the reservoir, the X component, the Y, and the Z is the vertical one. And of course Z is actually quite small in general. I mean the total signature is a few hundred microgal or a few hundred nanoG, but most of it's in the horizontal direction. That's pretty hard to measure. The vertical signals are much smaller, they're about tens to 30 microgal, a really good signal to try to measure. So actually by the dam wall is a pretty good location because you can get right under the water. But we're going to sort of, maybe later this year or early next year, start doing some measurements with Bridgeforth together with a side-by-side meter. And actually our location will be stuck in the side of the dam wall and the water's sitting up about here. And these are the sort of, these are the feedstocks down to the low reservoir, which is about 300 meters below. If we don't go soon, then this gets covered in snow, and it's a little bit harder to get up there. But we'll try to do that in the next few months. So, just about finished there. We've got a few minutes left. We can have some questions. What are we doing at the moment? Well, we're trying to build these devices. You can see that we can make these sort of low-frequency oscillators, 1 to 2 hertz silicon oscillators in MEMS. We can make them at any angle we want. So we are working on 3-axis devices. We're really pushing hard on the packaging. So we're working. We're going to be working fairly soon with Kelvin Nanotechnologies to actually develop the standard processing and actually package them with a company in the central belt of Scotland called Optica. Richard's not going to talk about this, but I've said about it already. Slides I've used before, of course. So we talked about the Kurokan reservoir work, but there's lots of interest in doing engagement across oil and gas, environmental monitoring, volcanology, and of course security and defence. Because these are small devices, you can get them onto drones. So I'll finish there, and happy to take questions on anything to do with suspensions, the MEMS stuff, whatever you like. Thank you.